Welcome to the HT8 MCU Basic Tutorial. In this session, we will be exploring Comprehensive Experiment 3, Comparator Usage. This experiment will be explained from the following 5 aspects, which are Comparator Usage Experiment Introduction, Hardware Connections, Program Development, Practice Results, and Experiment Summary. Comparator Usage Experiment Introduction. The learning objective of this experiment is to master both the comparator and ADC functions. Now, let's look at the experiment content. The comparator's positive input voltage is adjusted using a potentiometer. Its negative reference voltage is obtained through a voltage divider circuit. The positive voltage is fed to an ADC pin. After sampling by the ADC, the value is shown on the digital tube. The LED is illuminated when the positive input voltage is greater than or equal to the negative reference voltage. Otherwise, it is extinguished. In addition to the comparator, this experiment also uses several other peripherals: GPIO, ADC, internal oscillator, and the WDT function. Let's see what materials are needed for this experiment. This experiment uses the DEV3195 development board as the main control board. The emulator provides the 5-volt power supply. We will also use the following components: an LED, a potentiometer, a digital tube, a capacitor, resistors, a breadboard, a Type-C cable, and connection wires. Hardware connections. Next, let's go through the schematic diagram of this experiment. The main control MCU on the DEV3195 development board is the HT66V3195. A bypass capacitor is connected between the power supply and ground on the board, which helps stabilize the supply voltage and filter out AC noise. On the comparator's positive input side, a voltage divider is formed using a 1K ohms resistor and a 10K ohms potentiometer. By adjusting the potentiometer, we can change the positive input voltage. This voltage then passes through an RC filter before being sent to an ADC pin. The MCU samples it via the ADC and displays the value on the digital tube. On the negative input side, two 10K ohms resistors divide the voltage to provide a reference of half VDD. If the voltage comparison result between the two inputs changes, the MCU will trigger a comparator interrupt. It then controls the GPIO pin to update the LED status accordingly. On the right side of the schematic, you'll see 2 circuits. One for the digital tube display, and one for the LED indicator. We use a 2-digit common anode digital tube here. The comparator's positive input voltage is sampled by the ADC and shown on the digital tube. If the positive input voltage is higher than the negative reference voltage, the LED lights up. Otherwise, it turns off. For this experiment, we'll be using a breadboard. Below is the connection diagram for the setup. The power is supplied by the E-Link Pro 2 at approximately 5 volts. You can find the programming pins on the upper side of the development board. For in-circuit emulation or programming, you can use either the E-Link Pro 2 or the eWriter Pro 2 tool. Finally, here is a physical wiring photo of the breadboard for your reference. Program development. Now, let's look at the workflow within the MCU's main function. It includes the following steps in order: system clock configuration, WDT configuration, digital tube I/O configuration and initialization, LED I/O configuration and initialization, ADC configuration. Comparator configuration. Enable global interrupt. Clear the WDT. ADC sampling. ADC voltage conversion. And finally, digital tube display. The following describes the comparator interrupt function flow. After the MCU enables the comparator function in the main function, the comparator interrupt will be triggered when the voltage comparison result at its two inputs changes. Inside the interrupt service routine, it determines the relationship between the positive input voltage and the negative reference voltage. If the positive input voltage is greater than or equal to the negative reference voltage, the MCU controls the GPIO pin to illuminate the LED. Otherwise, it extinguishes the LED. Next, let's look at the program example. Here is the main.c file. This experiment uses two header files. The first, HT66F3195.h, contains definitions and declarations for the registers, ports, and peripherals of the HT66F3195 and HT66V3195 MCUs, which help us in programming. The second, stlib.h, provides functions related to numerical conversion, which are needed for processing ADC data. Before writing the program, we typically use macro definitions to declare the pins that will be used. This includes macro definitions for the digital tube pins, their output configuration, instructions to set these pins to low level, instructions to set these pins to high level, and similarly, the output configuration and control instructions for the LED pin. Next, we have the encoding table for the common anode digital tube. The MCU controls the digital tube's I/O ports by looking up this table to display the corresponding numbers. Using a combination of a struct and a union can make the program organization clearer and more efficient. Below, we define a struct and a union for storing the digital tube display data. Function declaration. It informs the compiler about a function's name, return type, and parameter list. This is necessary to resolve compilation errors that occur if a function is called before it is defined. Next is variable declaration and definition. This creates a variable by informing the compiler of its name and data type, and allocates memory for it. Now, let's look at the main function. First, it performs the initial configuration. This includes setting up the system clock, the WDT, the I/O ports for both the digital tube and the LED, as well as the ADC and comparator functions. Finally, it enables the global interrupt. Inside the main loop, it continuously performs three key tasks: clearing the WDT, carrying out ADC sampling, and refreshing the digital tube display. To eliminate errors in ADC sampling, the sampled value is only updated if it differs from the previous reading by more than 40. A difference of 40 in the ADC value corresponds to a voltage change of about 0.05 volt, which is suitable for achieving a result with a precision of 0.1 volt. This method effectively prevents the digital tube from flickering when the sampled voltage is near a critical threshold value. Now, we will introduce the individual sections of the main function, starting with the system clock configuration function. It uses the internal oscillator and is set to 8 MHz. Next is the WDT configuration function. It enables the WDT and sets its overflow period to 512 milliseconds. If this period is exceeded, the MCU will reset. Therefore, it is important to clear the WDT regularly during program execution. Moving on to the digital tube and LED I/O configuration function. First, set the I/O port source current to level 2. Then, configure the digital tube I/O ports to output mode. To turn off the digital tube according to its common anode design, set the dig pins to low level and the SEG pins to high level. Finally, set the I/O pin controlling the LED to output mode and turn the LED off. Now, the ADC configuration function. Set the PA4 pin as ADC input channel 3. Select the ADC clock as the system clock divided by 4, and then enable the ADC. Configure the ADC input signal to use the external analog channel input, specifically selecting channel 3. Set the ADC output data format to right alignment, and select AVDD as the reference voltage. Next is the comparator configuration function. Configure the multiplexed pins for comparator input function. Set the comparator for non-inverting output. Enable both the comparator hysteresis function and the comparator interrupt. Finally, turn the comparator on. Next is the ADC sampling function. First, declare the variables used within this function. Then, begin ADC sampling using a filtering method that takes 4 consecutive measurements and averages them. After each sampling cycle, read the ADC value from the register and add it to an accumulator. After 4 consecutive samples, end the ADC sampling and calculate the average value. Next is the ADC voltage conversion function. It converts the ADC value into the actual voltage using a conversion formula. The following explains the ADC conversion formula. Since it is a 12-bit ADC and AVDD is 5 volts, the initial voltage formula is derived. To keep 1 decimal place, the result is multiplied by 10, giving the second formula. Because a shift operation executes faster than division, it is used instead. This final formula is the one implemented in the program. Next, the digital tube display function. It is divided into an integer display part and a decimal display part. It controls the digital tube's dig pins via I/O ports to select whether to illuminate the integer digit or the decimal digit. The corresponding data is displayed on the digital tube by looking up the encoding table. After each display cycle, a delay is inserted, and the digital tube is turned off. This prevents the data for the integer and decimal parts from interfering with each other, achieving the purpose of eliminating ghosting. Now let's look at the comparator interrupt function. This interrupt is triggered whenever the voltage comparison result between the 2 inputs of the comparator changes. Inside the interrupt, it reads the status bit to determine the comparator's state and then controls the LED, turning it on or off accordingly. That concludes our introduction to the program example. Practice results. After the MCU is powered on, the digital tube displays 0, indicating that the current positive input voltage is 0 volt. We can observe that the LED lights up when the voltage is greater than or equal to 2.5 volts. Conversely, the LED turns off when the voltage is less than 2.5 volts. Experiment summary. This comprehensive experiment utilizes multiple peripheral functions of the HT8 MCU, including the following 5. The comparator, ADC, GPIO, internal oscillator, and the WDT. The hardware circuits consist of a voltage divider circuit, a digital tube drive circuit, and an LED drive circuit. Software processing of ADC data enhances the reliability of the ADC function, incorporating filtering and error elimination. As a 2-digit digital tube is used, a dynamic display method is required. Rapid voltage changes can easily cause ghosting on the digital tube, necessitating the operation to eliminate ghosting. Holtec has a professional service team to assist in development design and after-sales service. Please feel free to contact our business departments for more detailed product information and consultation services.